Dear students, uh, let us continue the Linux system. Today we will discuss about memory management in the Linux system. So let us begin with what is memory management. So we already learned about the paging concept. See, before executing any program, we need to bring a program from secondary storage device into main memory. And we know that a user program will be divided into the number of logical pages, and the physical memory or main memory is divided into frames. So here we need to bring logical pages into main memory. So that is what we need to map logical pages to free pages in the main memory. So logical pages must be allocated to free pages in the main memory. So that is what memory management. So Linux physical memory management system deals with allocating and freeing pages, groups of pages, and small blocks of memory. It has additional mechanism for handling virtual memory. So in case of Linux system, a memory mapped into address space of running processes. In Linux system, the memory is split into three different zones. They are namely zone underscore DMA, zone underscore normal, and zone underscore high memory. So zone underscore DMA is basically used for direct memory access, and its physical memory is basically less than 16 megabytes. That is, first 16 megabyte of physical memory consisting of zone underscore DMA, that is called as direct memory access zone. And the zone underscore normal identifies the physical memory that is mapped to CPU address space. So here it will be from 16 MB to 896 MB. It is called as the normal zone. So normal zone is basically a physical memory that is mapped to the CPU address space. So it is up to 896 MB from 16 MB. Less than 16 MB is called as direct memory access zone, DMA zone. And the memory above 896 MB falls under high memory zone. So it is called as high memory zone. It refers to physical memory that is not mapped into kernel address space. And each of these memory zone has its own allocator, which is responsible for allocating and freeing all physical pages for that particular zone. For example, if we take 32-bit Intel architecture, where we can address 4 GB of memory, that is a 2 raised to 32 provides 4 GB address space. Here the kernel is mapped into the first 896 MB of address space, so that is what normal zone. The remaining memory, that is the memory above 896 MB, is referred as high memory and is allocated from zone underscore high memory. Splitting of memory in a buddy heap. See, once a particular memory page is freed, we'll get free frames in the physical memory. So in case of budding heap, the allocator uses the buddy system to keep track of available physical pages. So available free frames can be maintained with the help of a buddy system. So in this particular scheme, adjacent units of allocatable memory are paired together, hence the name is given as buddy. Whenever two allocated partner regions are freed up, they are combined to form larger region that is called as a buddy heap. So we can see in the diagram. First, what we did is suppose that there are free frames of 4 KB available, and the two adjacent units of free frames are combined into form a larger memory chunk. So 4 KB has been combined to form 8 KB. So already 8 KB is there, and the two 8 KB memory memories have been paired up to form 16 KB. So this is called as a buddy heap. Now let us see how to manage the physical memory. So there is a physical page memory allocator. Here the page allocator allocates and frees all physical pages. It can allocate ranges of physically contiguous pages on request. The page allocator uses a buddy heap algorithm to keep track of available physical pages. Each allocatable memory region is paired with adjacent partner in the buddy heap algorithm. Whenever two allocated partner regions are freed up, they are combined to form a larger region. If a small memory request cannot be satisfied by allocating an existing memory-free region, then large free region will be subdivided into partners to satisfy the request. The memory allocations in the Linux kernel occur either statically or dynamically. And also Linux uses the slab allocator for the kernel memory. Now let us look at the slab allocation. So this is another strategy adopted by Linux for allocating kernel memory. So that is known as the slab allocation. A slab is used for allocating memory for kernel data structure and is made up of one or more physically contiguous pages. Here, a cache consists of one or more slabs, and there is a single cache for each unique kernel data structure. For example, a cache for the data structure representing process descriptor, a cache for file objects, a cache for semaphores, and so on. Each cache consisting of objects that are instance of the kernel data structure and cache representations. For example, the cache representing semaphores stores instances of semaphore object, and the cache representing process descriptor stores instances of process descriptor objects, and so on. The cache relationship among slabs, caches, and objects we can observe in the diagram here. In this figure, the two kernel objects of 3 KB in size and the three objects are 7 KB in size. So these objects are stored in the respective caches of 3 KB and the 7 KB objects in the cache memory. Then they are mapped to the physical memory slabs which are arranged in the contiguous manner. The slab allocation algorithm uses caches to store kernel objects. When a cache is created, a number of objects which are initially marked as free are allocated to the cache. The number of objects in cache depends on size of the associated slab. So in Linux, a slab may be in one of three possible states. First one, full. All objects in the slab are marked as used. Second, empty. All objects in the slab are marked as free. Partial. The slab consists of both used and free objects. Here the slab allocator first attempts to satisfy a request with the free object in a partial slab. If nothing exists, a free object is assigned from the empty slab. If no empty slabs are available, a new slab is allocated from contiguous physical pages and assigned to the cache. Memory for object is allocated from this particular slab. So that is how the slab allocation algorithm works. Now let us look at virtual memory. The virtual memory system maintains the address space visible to each process. it creates the pages of virtual memory on demand and manages the loading of those pages from disk or their swapping back out to disk as required. We know that swapping in and swapping out operations will be carried out. So that is what page replacement things we already learned. The page which is not used currently can be swapped out to the backing storage or disk, and the page which is demanded or the page fault occurred can be brought from disk to the main memory. So in this case, we make use of virtual memory concept that we already studied. The VM manager maintains the two separate views of a process address space. First one, a logical view. Second one is physical view. A logical view describing instructions concerning the layout of address space. The physical view of each address space which is stored in the hardware page table for a process. The virtual memory regions are characterized by a backing store, which describes from where the pages for a region come. Regions are usually backed by a file or by nothing, that is demand zero memory, and the region's reaction to writes, so that is page sharing or copy on write. In the Linux system, kernel creates a new virtual address space. We know that when a process runs a new program by exec system call, the kernel is going to create a new address space for that particular process. And upon creation of a new process by force system call also, kernel is going to allocate a new address space for the newly created process. On executing a new program, the process is given a new and completely empty virtual address space. The program loading routines use this address space with the virtual memory regions. And creating a new process with fork consisting of creating a complete copy of existing process virtual address space. Here, basically, the kernel copies parent process virtual memory address descriptor, then creates a new set of page tables for the child process. The parent page tables are copied directly into the child's address with the reference count of each page covered being incremented. After the fork, the parent and child share the same physical pages of memory in their address space. Next, the virtual memory paging system relocates pages of memory from physical memory out to disk when memory is needed for something. The virtual memory paging system can be divided into two sections. First one, the page-out policy algorithm decides which pages to write out to disk and when. Second one, the paging mechanism actually carried out the transfer and pages data back into physical memory when it is needed. Now let us see executing and loading user programs. So Linux is maintaining a table of functions for loading user programs. It gives each function the opportunity to try loading the given file when an exec system call is made to run a new program. The registration of multiple loader routines allows the Linux to support both ELF and A.out binary formats. Initially, the binary file pages are mapped into virtual memory, and an ELF format binary file consists of a header followed by several page aligned sections, as it is shown in this particular diagram. So at the top we can observe kernel virtual memory. It is used by the kernel in the kernel mode, which is not visible to the user mode code or user programs. Followed by kernel virtual memory, there is a stack memory, so which is growing here. So stack memory is basically used for temporary storage. We know that. and after that you will find the heap memory, where actually we will have the memory map region that is growing in the opposite direction of stack memory. And when a program is brought into the memory, in case of ELF, we'll have the different segments in the memory, like program text will be present in the text segment, followed by initialized data segment will find here, where initialized data is present of the program. And after that we have uninitialized data segment, where actually the uninitialized data of the program is kept here. And we have got the runtime data. So the data which is generated during execution of the program will be stored here. So that is called as runtime data. So it is basically comes under heap area, and it is going in the upward direction. And below this there is some region that is called as the forbidden region. Now let us look at static and dynamic linking. So what is linking? So that already we studied. So during execution of program, the program must be linked with the system libraries. So there are two ways of doing this: static linking and dynamic linking. So Linux is supporting both static and dynamic linking. A program whose necessary library functions are embedded directly in the program's executable binary file is called as static linking. The main drawback of static linking is that every program generated must contain copies of exactly the same common system library function. So in every program what we do is a separate copy of a library has been included. So that increases size of the program. But in case of dynamic linking, there is only one system library is maintained, and it is dynamically linked to the program during execution time. Hence, the dynamic linking is more efficient in terms of both physical memory and the disk space usage, because it loads the system library into memory only once, and it can be dynamically linked with the program whenever required. Hence, they are efficient as compared to static linking. So, this is the end of memory management in Linux. Thank you.